Welcome back. This is the day the Lord's made. Let your dress me glad it. In this video, I'm going to talk about Gibbs free energy. So this is the next part of talking about enthalpy and entropy. So quick review. Enthalpy is all about energy changes for chemical reactions. Entropy is all about disorder changes in a chemical reaction. So anyway, Gibbs free energies can be taken into account both those things and telling us whether the reaction takes place or not. So it's going to take into account energy changes and disorder changes and determine, do we expect this reaction to take place on its own? So again, in general, reactions tend to want to happen if they get to lose energy, which is basically like you. If you can have less energy, you would rather do that. Can I be lazy? I'd rather be lazy than working hard. All right, if you want to be lazy, that's spontaneous. That's what you favor. Working hard takes effort, so it's not quite as favorable. So chemicals, same way. If they can get rid of energy, that tends to be something that's favorable for them. They also tend to be favorable for the reaction if it makes it more disorderly. So if it can be messy, if it can be spread out and all over the place. So if it increases the disorder, that's favorable. So if it can be lazy and it can be sloppy, it's going to happen. All right, this is just what's generally going to happen. So if a chemical reaction has a negative H, which means it gets rid of energy, and a positive S, which means it gets to be more disorderly, it's going to be spontaneous. It will happen on its own. It doesn't need any assistance. Now, this doesn't say how fast it takes place. It just says it will take place. So it doesn't say that just because something is spontaneous doesn't mean it's boom, all done immediately. It might be something very slow. Like, for example, iron rusts. Iron will rust spontaneously. You don't need to try to help it. If you take some iron, put it outside, leave it out there for a while, it'll rust. You don't need to try to help it. It's spontaneous, but it's still a relatively slow reaction. It doesn't rust really quickly. So, all right, next thing, if it's a positive H, which means it takes energy and it makes it orderly, it's non-spontaneous. It doesn't happen on its own. All right, you can think of this like cleaning your bedroom. Cleaning your bedroom would take energy from you. It would take an input of energy, positive H, and your room gets more orderly. So does it happen spontaneously? Probably not. Now, again, when we say something's non-spontaneous, it doesn't mean it can't happen. It just means it needs something to assist it. It needs something from outside the system to help it out. Something else providing some motivation to the molecules, okay? So if there's a disagreement, meaning like, if they can't both agree, because in this two first examples, they both agreed. This is both favorable, this is both not favorable. If there's disagreement, it comes down to the temperature, which is the energy available. The general rule is if a chemical reaction is a negative H and negative S, it happens at low temperatures. All right, and if it's a positive H, positive S, it happens at high temperatures. So it might make more sense to talk about the second one here. Why would this happen at high temperatures? So this reaction will make it be more disorderly. That's great. We get to be messy, but the reaction takes some energy. So that means we need to have enough energy to be motivated to make the mess. And so if the chemical reaction has plenty of energy to go around, i.e. high temperatures, then we can overcome this deficiency here. Be like, you know what, we got plenty of energy. Sure, let's make this happen. Okay? So putting them all together again, sometimes I make the analogy between guys and girls and couple. What's going on here? Let's see. So if he says no and she says yes, so he says thumbs down, she says thumbs up, what's going to happen? It always happens. He's like, I don't know if I like that idea. And she says, I think this is a great idea. We should rearrange the kitchen this way or I've been thinking about rearranging the living room. It's going to happen. All temperatures. What if he's like, but I thought we could make this room turn into a man cave. I think that'd be great. And she says, I don't think so. It's not happening. All right. So if they disagree, it's whatever she says. So if she says yes and he says no, it's always happening. If he says yes and she says no, it's never happening unless you get some outside assistance. Maybe some guy friends can help you out there. Anyway, if they agree, they both are negative, then it happens at cold temperature. She thinks it's like negative degrees Celsius. Cold meaning negative degrees. And positive, spontaneous at high temperature, so like above freezing, positive temperatures. So Gibbs free energy is going to basically take these two ideas here, enthalpy and entropy, and bring it together in a mathematical relationship. It's basically taking account how favorable different things and do we have the energy for it to take place. So we know what you want to happen. Do you have the funds, the free energy to do it? So is there enough available energy to make this take place. So it's going to basically be an equation taking into account the enthalpy changes and entropy changes. So here is our equation for that. The Gibbs free energy is going to be equal to the change in enthalpy, which would be the change in energy for the reaction, minus the temperature times the change in entropy. So this is basically Gibbs free energy, how you'd calculate it using a change in enthalpy and a change in entropy. So again, G up here would be, if we abbreviate this, G, Gibbs free energy in joules or kilojoules. This is enthalpy. This has, now do take note, this temperature must be in Kelvin. Entropy and enthalpy tend to be in different units, so watch out for that. So if you get a negative G means that the reaction is spontaneous. When you plug everything in up here, if you get a negative G, that means the reaction takes place. If you get a positive G, it means it's non-spontaneous. It will not happen. If you get a G of 0, that means that it's at a turning point where it's going to be changing. So for example, water at 10 degrees Fahrenheit spontaneously will freeze. Water at 50 degrees Fahrenheit will not spontaneously freeze. So the value of G changes over the course of the temperature. So at like 32 Fahrenheit, G would be 0 for water, because that's a place where the water could go either way. All right, so when G is 0, that's like when you're changing. And that'll be really important to remember when you solve some of the questions, because if it says, where's the boiling point, you'll be like, okay, well, I know G is 0. If it's asked for what the freezing point is, like, oh, I know G is 0. And then I can use other information to solve for that. It should also be noted that on a data table, Gibbs energy is 0 for standard state, just like enthalpy. So silver, be a solid. Okay, takes no energy. And we've, by definition, the Gibbs energy is 0 as well. We're saying, okay, that's how you're supposed to be. And S's are different. Do take note again, H kilojoules, S tends to be in joules, G is usually measured in kilojoules as well. So here's a couple sample questions for us to work it out. So these are like B-level questions here for chemistry. So where sample question, the below reaction has an enthalpy change of this value here and an entropy change of this value here. What's the freezing point? Answer in Kelvin. So again, the big idea is the Gibbs free energy equation allows us to solve for what the value of G is and also find out whether it's spontaneous or not. Here, we know the value of G is going to be 0 because we're looking for the freezing point. So something going from a solid to a liquid, we know that G is 0 at that temperature. At whatever temperature this thing changes phase, G is 0 because that's where it stops being spontaneous or starts being spontaneous. So we have the H value, the S value, and we know the G value. Notice that since these things are different, we have kilojoules and joules, we got to convert one. So in my example down here, I converted the S to kilojoules. So how do you do that again? Take that 135 here divided by 1,000, that puts you in kilojoules. So Gibbs free energy is 0 because we're changing spontaneity. Change enthalpy given 32.1. We're looking for the temperature, and our change entropy was this right here. So we arrange, solve for that. So we subtract 32.1 from both sides, divide. That is the temperature at which it'll be spontaneous, or we should say where it changes. So what does this mean? If we find our temperature to be 238 Kelvin, that means if it is colder than 238, the substance will spontaneously be a solid. If it's above 238, it'll spontaneously be a liquid. All right, next question. Chemical reaction has a 15.2 kilojoule change in enthalpy, meaning it took energy to do, and it has a negative 68.8 joules per Kelvin entropy change. So it got more orderly. What is the value of Gibbs free energy at temperature 580? Quick note, we see that we have a positive H, negative S. That means this reaction does not happen. It's not spontaneous. We expect to find a value that is a positive G. That's also something too you can double check your work on. Like I expect G to be positive or negative based off the signs of H and S. So we're given the H, given the S, given the temperature, we want Gibbs. Note that it wants Gibbs in kilojoules per mole. So we'll just turn the joules again into kilojoules and solve, this time solve for Gibbs energy. We're looking for that. We have the change in enthalpy. We want to know what temperature, we already have the temperature, got the change in entropy. Find a Gibbs energy of 55.1. So watch out when doing the homework assignment. Sometimes it'll have Celsius or Kelvin. Just keep an eye on that. In this equation, this temperature must be Kelvin. Also take note that the Entropy one usually is in joules, and so divide that by 1,000 to turn that into kilojoules. Okay. One more thing I should mention too, like before, you can also find the G by doing the products minus reactants. Meaning you could find the G if you know the G values for the products and the reactants, just like we did with enthalpy and entropy. So you could look at the data table, take the G values for the products and the G values for reactants to find the overall change in G. Of course, that would be just for that temperature on the data table is 25 degrees Celsius. So do take note, that is also something you can also do. One more thing, let me just do a little quick review for all of these things here. And we'll just predict the signs for water at different temperatures. All right. So let's pick a temperature, 50 degrees Celsius. So what are the signs of H, S, and G for this phase change, for this reaction here at 50 degrees Celsius? So we're going from a solid to a liquid. We're just taking solid water, turning to liquid water. What's the sign of H? Well, if you want to turn a solid, turn into a liquid, that's going to take energy. We expect this to be a positive H. All right? What's the sign of S? If you go from a solid to a liquid, we're getting more disorderly. Getting more disorderly means that it is going to be a positive S. We're going to get more disorderly because liquids are more disorderly than solids. What is the sign of G? Does water at 50 degrees Celsius go from a solid to liquid on its own? Which means if I took an ice cube and put it into some place that's 50 degrees Celsius, would it melt? The answer is yes. The sign of G would be negative G. We'd expect this to happen. It'd be pretty warm. The ice cube should melt. And let me do another one. Sorry, I didn't have this one ready here. I was inspired. All right, so we're gonna do the same thing here and ask ourselves, what do we expect to happen? What is the sign of H? What is the sign of S? Oh, we should also talk about when do we expect this to be spontaneous or not. We didn't do that up here. Come back up to this one here for a second. When is this spontaneous? We have a positive H and a positive S. This is spontaneous at what? Spontaneous at high temperatures. Again, what temperature would that be? It'd be anything above 0 degrees Celsius. So again, when we say high temperatures, it's above a certain point. So in this case here, it'd be 0 degrees Celsius. This one here, what do we got going on here? What's the sign of H for this? You might not recognize this. This is propane. What happens when you burn propane? Propane plus oxygen, that's very exothermic. We'd expect this to have a negative H. All right, we're going to be giving off a lot of energy. We're going to take some 6 gases, turn into 7 gases. That's an increase in the amount of gas we have. That is a positive S, which means that we expect there to be more disorder, which again, almost always, anytime you have a combustion reaction, there's a positive S. You are making it more disorderly. When's the last time you burned something and it got more orderly? Doesn't happen. All right, so negative. So what's the sign of G here? So we have a negative H and a positive S. So under these conditions, I didn't even put a temperature. We don't need to have a temperature. This will be a negative G at all conditions, meaning that no matter what the temperature is, oxygen and propane will react. All right, so it doesn't matter what the temperature would be, we can make that prediction. All right, God's peace.